In this video, we're going to be solving 5 AP Bio problems for Unit 5 Genetics. So we have a pea plant that is heterozygous for seed color and seed shape is crossed with another heterozygous plant. Yellow Y is dominant to green, lowercase y, and round uppercase R is dominant to wrinkled lowercase r. The cross is YYRR and YYRR. We want to find the probability that the offspring will be green and wrinkled. Let's write again what we have for yellow. This is when you have Y dominant. Green means you have Y recessive. Round means that you have R dominant. And wrinkled means you have R recessive. So our cross, again, is YY x YYRR x YYRR. So we want to find green and wrinkled. The fastest way that you can do this is you are going to separate your traits. So we have YY against the YY here. So we have Y, Y, and Y, Y. So in our table, this is a lowercase y. So you can cross these and figure out the phenotypes that you're going to get and genotypes. So you are going to get uppercase Y, uppercase Y, uppercase Y, lowercase y, uppercase Y, lowercase y, and lowercase y, lowercase y. So you have Y is 1/4 of your scenarios. And then for RR, you have uppercase R, lowercase r, and you have uppercase R, lowercase r. So then you get RR, 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 RR. So then you have RR as 1/4 of your scenarios. So we want to find and. So because we have and, we have to use the and rule, which is multiplication. We're going to take 1/4 and multiply that by 1/4. You can multiply these 4s together, and then you just get 1/16. So the chance of getting both green and wrinkled is 1/16. So just to backtrack, we found the probability of us getting green on its own, which is 1/4 of our chances, and then we found the probability of getting wrinkled, which is 1/4 of the chances. And then in order to find the probability of getting both of these together, you have to multiply the individual probabilities against each other. So then we have an organism with a genotype AA. BB is crossed with AABB. Traits A and B are dominant. Find the probability that the offspring will show the dominant phenotypes. So this is another dihybrid test cross where A and B are going to be dominant traits that mask our lowercase letters. So we are trying to find the cross of AABB x AABB. Again, we're going to split this by gene by doing our A's and our A's against each other. So we have uppercase A, lowercase a against lowercase a, lowercase a. So creating our table, we can multiply. We have uppercase A, lowercase a, uppercase A, lowercase a, lowercase a, lowercase a, lowercase a, lowercase a. So in total, we see that we have AA in 1/2 of our scenarios, and this is dominant. So, and we also have AA lowercase in 1/2 of our scenarios, and we know that this is going to be recessive. Now we'll do the same thing for BB. So you're going to have uppercase B, lowercase b, and you have lowercase b here, lowercase b. So then we can cross these. We are going to have uppercase B here, lowercase b, uppercase b, lowercase b, lowercase b, lowercase b, and lowercase b, lowercase b. Now we see that we have this BB, which is our dominant 1/2 of our scenarios. And then we have lowercase b, again 1/2 of our scenarios, and this is going to be our recessive. So in order to find our both dominant and see when we are going to get both dominant types, we are going to multiply the 1/2 and times our other 1/2. So we multiply the probability of getting a dominant A, and also the probability of getting a dominant BB together in order to find the probability of getting the dominant together. So that is going to equal to 1/4. So each of the traits individually, they have a 1/2 a chance of showing the dominant phenotype. So then in order to find the probability of getting both, you just multiply. So a trihybrid cross is performed where we have AABBCC and AABBCC. We want the probability that the offspring will have the genotype AABBC, meaning that the homozygous recessive for A and heterozygous for B and dominant phenotype for C. So this means that for AA, BB, and C, this dominant phenotype is either going to be CC or CC, since we have a blank there. Now, the fastest way again to do this is by separating by gene. So let's write this down again. CC, XAA, BB, CC. So these two, you are going to have uppercase A, lowercase a, and here you have uppercase A, lowercase a. So this gives you AA, AA, and AA, AA. We get AA 1/4 of the time. Now what about our B gene? We get B, 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 B. So we get BB, 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 BB. So we get our heterozygous combination, BB, in 1/2 of our scenarios. And then finally for our CC, we have uppercase C, lowercase c, and you have this crossed against uppercase C, lowercase c. You get uppercase C, 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 and you get CC. So this is going to be your dominant case scenario, C, where you have a blank C, or when you have CC, that is going to compose of 3/4 of your scenarios. That's your dominant scenarios. So now we just have to multiply these against each other. We have 1/4 against 1/2 and against 3/4. So that's going to give you 3/32. So we can see that each of these genes are inherited independently, and each child must satisfy all 3 genotype and phenotype conditions. So now we have color blindness in an X-linked recessive trait. We have a carrier female, XN, and XC is crossed with a normal male, X to the power XN, Y. And we want to find the probability that they are going to have a recessive son. So in this case, we have a sex-linked recessive cross. And we are having a carrier female, and we have a normal male. So our carrier female is XN, XC, XX is female, and then normal we have XN, Y. So crossing these, we have to find the probability of an affected son. So for our Punnett square, let's write this out. We have XN from dad, and we have Y from dad. So this is going to be against our mom. We have XN from mom, and you also have XC from mom. C being the... Okay, so now you're going to have XN, XN. This is going to be a normal daughter because N is for normal. We have XN, XC. We have a carrier daughter. And we have XNY. We have a normal son. And then we have XCY, where we have an affected son. So we can see that our affected son, which is XC, Y, is going to be 1/4 of our scenarios. So then if we have the question here, we just are going to say 1/4. Now, if the question said that, if we're asked for the child that is a male, that's just 1/2 of our possibilities. 1/2 of the children are going to be male. That's just for any cross against a mother and a father. So we have to get our Y from dad and X from mom. So that means that the sons who receive the mom's recessive X, they're always going to be affected. So for our last question, we have cystic fibrosis is an autosomal recessive disorder. We have 2 unaffected parents, and they have an affected child. What is the probability that their next child will be unaffected but a carrier? So cystic fibrosis, again, is autosomal recessive. So we want to find our parents first. Our parents, in order to have 2 unaffected parents and to have an AA child, that means that both of your parents, they had to be carriers. So we can determine that the parents were AA and AA. So if we create our Punnett square and we cross these two, we have A against A, and we have AA here, we have AA here, AA here, and lowercase aa here. So what we can see is that AA composes 1/4 of our possibilities, and these are going to be our unaffected non-carriers. We can see that AA heterozygous is 1/2 of our cases, and these will be our unaffected carriers. And we can see our AA lowercase. These are going to compose 1/4 of our cases, and these are going to be our affected children. So if you have AA, that's 1/2. So this is your answer, 1/2 of your scenarios. So something important is that if the question asks what the probability is an unaffected child is a carrier, then we have to remove AA lowercase because we already know that the child is unaffected. So then our possible unaffected outcomes are going to be AA, AA, AA. So then our carrier among the unaffected is going to be 2 out of 3 of our possibilities. So without our extra information, the carrier probability is 1/2. But if we already know that we have an unaffected, that affected lowercase aa outcome is removed, making the carrier probability just 2/3.